Multiplicity, which is sometimes referred to as peak splitting, results from magnetic effects that neighboring protons have on each other. So let's focus on HA and HB in this example. These protons have their own chemical environment and will give their own signals in an NMR spectrum. Now focusing solely on HA, let's see how the presence of HB can affect the signal that appears for HA. Now we know that protons can align with or against the external magnetic field. So for HB, it can adopt two different spin states. We either have the beta spin state where it's against the magnetic field, or we have the alpha spin state where it's with the magnetic field. Now we know that it's constantly jumping back and forth between these two spin states and putting it in a different electronic environment. So since there are two possible electronic environments for the HB proton, it can affect HA's signal in two different ways. So the signal for HA is actually going to appear as two peaks, which is known as a doublet. Now let's consider a second example where HA has two neighboring hydrogens, both labeled HB. So for HA, it can be affected by the different spin states that each one of these HB protons adopts. So either both protons can align against the magnetic field, so we can have them in the beta spin state. We can have one with and one against, and we can have that in opposite forms. So we can have either the top HB in the beta spin state and the bottom one in the alpha, or vice versa. We can have the top one in the alpha and the bottom one in the beta. So these are two possible scenarios. Or we can have both HB protons aligned with the magnetic field in the alpha spin state. So since there's three possibilities of electronic environments produced by the HB protons, we're going to actually have the signal for HA appear in three different ways. Now this is known as a triplet. So this entire signal here represents HA, but because it's split into a triplet, it means that it has two neighboring hydrogens. The purpose of multiplicity is to tell us the number of neighboring hydrogens a group of hydrogens can have. So these are examples of the different ways that our peaks could be split. So when it is not split at all, this is known as a singlet peak, and a singlet peak represents a hydrogen or group of hydrogens that have no neighbors. When it's split into two, this is known as a doublet. A doublet represents a hydrogen or a group of hydrogens that have one neighbor. When it's split into three, it's a triplet, and it would represent something that has two neighbors. 4 is called a quartet, and it would represent three neighbors. 5 is known as a quintet, which would represent 4 neighbors. Sextet is when it's split into 6, and that would be 5 neighbors. And finally, we have a septet that would represent a group of hydrogens with 6 neighbors. Now these are just a few of the examples. It can continue going on, octet, nonet, etc. There's also an example of splitting called a multiplet. A multiplet is not a set number of splits that are easily counted. So a multiplet usually occurs when you have different types of neighboring hydrogens that cause multiple splitting. Now, there's two different ways to look at multiplicity, and it all depends on what you're trying to do. So to predict the splitting that you would expect using the structure of a molecule, what we do is use the n+1 rule. So n represents the number of neighboring hydrogens for a group of hydrogens. If we add 1 to that, we would expect that number of splitting. So for example, if a group of hydrogens has one neighbor, if we add 1 to that, we would expect the signal for that group of hydrogens to be split into 2, which would represent a doublet. Alternatively, if you're looking at NMR data and you're trying to determine the number of neighbors from the NMR spectrum, you would look at the splitting and subtract 1. So essentially, we're just taking this simple formula and we're moving it around so that the splitting that we observe, -1, equals the number of neighbors. So that's what we kind of see up here. So for example, with the quartet, we see the splitting is 4. Now if we subtract 1 from that, we get 3, which is equal to the number of neighbors. So it all depends on what data you're looking at or what you're trying to predict, but these are the simple formulas that you can use. There are two main rules when it comes to multiplicity. The first one is equivalent protons cannot split one another. So if we look at these two groups of H's, these are actually equivalent H's. They are both bound to a carbon that's bound to a chlorine that's bound to another carbon. They can be described in exactly the same way. So these sets of hydrogens will actually appear as one signal. And as a result, they cannot produce any sort of splitting because they are completely identical. So in order to have splitting occur, the neighboring protons must be different. They must produce a different signal. Second, in order to split each other, protons must be within a 2 or 3 bond distance. So examples of that are a geminal arrangement, where the two different protons are attached to the same carbon. This scenario is fairly rare. We're not really going to encounter many molecules with this type of geminal arrangement. Most common is the vicinal arrangement, where we have the protons 3 bonds away, or essentially they are on neighboring carbons. But examples of this, where you have HA that's a full carbon away from HB, we have a total of 1, 2, 3, 4 bonds between these two hydrogens. So these two are too far apart, and you would not observe any sort of splitting with the signals associated with these hydrogens. Splitting is not observed for certain types of protons. For example, the H attached to the oxygen in an alcohol, or an ethanol in this case, does not participate in splitting. Now the reason behind this is that this H is known as a labile hydrogen, and so it's easily removed and exchanged with other hydrogens either in the solvent or in other alcohol molecules. As a result, this H does not stick around long enough to cause any splitting for the neighboring hydrogens on these carbons over here. So alcohols typically do not show splitting with their peaks. So for instance, this H, the signal appears here. So you can see it appears as a singlet. Now that doesn't mean that the hydrogen doesn't have any neighboring hydrogens. It does have two neighbors over here. It just means that it's a special type of proton that does not participate in splitting. So this hydrogen will not show any splitting in its signal, and it will not be considered a neighbor for this group of hydrogens here. So for instance, if we draw in these two hydrogens on this carbon, we're really only going to pay attention to the 3 neighboring hydrogens we have on this carbon over here. And sure enough, if you look at the peak representing, let me change the color. If we look at the peak representing those 2 hydrogens, it is split into 4. And that's because it has 3 neighbors plus 1 means that it's going to be a quartet. So essentially with the alcohol hydrogens, they're not participating in the splitting rules. Other types of hydrogens that do not participate are carboxylic acids. These ones are mainly because they're too far away from any neighboring hydrogens. For any of the closest hydrogens, it would still be 1, 2, 3, 4 bonds away. For aldehydes, it's very rare that they participate in splitting. Occasionally, you might see some minor splitting with hydrogens that are very close by within that 3 bond range, but again, it's very rare. Amines are very similar to alcohols. So amines are also labile hydrogens, and so they're easily removed and exchanged with the solvent that the NMR is being run in or with other amines. So these guys we typically don't see splitting. So amines are very similar to alcohols. The NH protons generally appear between 0.5 and 5 ppm in the proton NMR spectrum. So it really is variable. It's not a set number that we would expect. Now with the amine protons, they can be affected easily by the solvent, concentration, and temperature. So all of these can influence the chemical shift of where these peaks appear. Now, we just learned that NH protons don't give any splitting or don't participate in multiplicity, and they generally give broad signals. So again, they're very similar to OH protons. So OH protons can also give broad signals with no splitting. Now, we just learned that the H's on amines are capable of being exchanged with other H's in the solution. Now, if deuterated water is used as a solvent, and deuterated water is when the hydrogen in H2O has been replaced with its isotope deuterium. Now, in this case, these deuterium atoms can exchange with the H's on the ends, and eventually the D is going to replace the H. Now, since deuterium has an even mass number, it's not detected by the NMR machine. So after enough of the exchanges, and we have a bunch of ND peaks or ND bonds, the proton peaks will actually disappear completely. And that's because any sort of atom attached to the nitrogen, which is in its deuterium isotope, is not going to be detected. Now, as far as the chemical shifts for neighboring hydrogens to an amine, nitrogen is an electronegative atom, so it is going to pull the electron density towards itself. So we do see a pretty big shift in terms of the chemical shift of the neighboring protons. So typically these protons come out at around 1.2 or 1.3. When they are on the alpha carbon next to the amine, they're going to be shifted up to about 2.7. Now, as we get further away from that amine, we're going to have less of a chemical shift. It's also useful to be able to analyze the aromatic protons in an NMR spectrum. So aromatic protons are the hydrogens directly attached to a benzene ring, and they tend to show signals in the 7 to 8 ppm range. Now, these are one of the few sets of protons that come out in that range, so it is useful to look there to see if you have the possibility of a benzene ring. Now, typically with a monosubstituted benzene ring, meaning a benzene that has one substituent, and in this case we have an ethyl group attached, we'll take a look at all of these protons. Now, technically we have three different types of protons in this benzene. We have the two that are closest to the ethyl group, two that are a little further away, and then one that's the furthest away. Now, because the aromatic protons are so deshielded, they tend to have their signals overlap with one another. So we actually see one large group of peaks representing all 5 hydrogens, even though they're technically different. Because these signals are overlapping and we have different splitting occur, it's not very easily distinguishable. So we can go ahead and call this a multiplet peak, meaning we have multiple hydrogens with multiple patterns of splitting. Now, other types of patterns that are easy to distinguish occur with disubstituted benzene rings. So here we have a benzene ring that is para-substituted with two identical groups. Now, because of the symmetry in this benzene ring, all of these hydrogens are completely identical. So they will actually appear as one singlet representing all 4 hydrogens. There is no splitting because equivalent hydrogens cannot split one another. Now, in a para-substituted benzene ring with two different groups, we get this type of pattern of two sets of doublets. And that's because the hydrogens that are closest to X represent one type of group. The hydrogens closest to Y represent a different one. So the red hydrogens will be split by one neighbor of the blue hydrogens, so they will become a doublet. And the blue hydrogens have one neighboring red hydrogen, so they will also be doublets. Now, depending on the identities of X and Y, that will influence which doublet represents which. If X is an electron withdrawing group, it's going to shift the peaks for the red hydrogens further to the left. So that could represent the set of doublets on the left. If Y is an electron donating group or not as electron withdrawing as X, then that will shift these further to the right. So that would represent the peaks on the right. So these are two typical patterns that you would see with the para-substituted benzene rings. To go even further into multiplicity, we can take a look at J values. And J values will actually measure the distance between the splits in a group of peaks. J values is a very complex topic, and it's not going to be necessary to solve most of the problems you're working with in this class. However, it's a useful tool because it can give us a hint as to whether or not H's are right next to one another. So pretty much the J value or multiplicity measures the degree to which a neighboring proton will shield or deshield its neighbor. Now when protons split each other, their coupling constants will be equal, and the coupling constant is another term for J value. So in this example, HA is neighbors with HB. HA will cause splitting for HB, and HB will cause splitting for HA. Now because these two are splitting one another, if we were to go through and actually measure the distance between each of these splits, we would find that they would be exactly the same. Now the peak for HA is currently a quartet, and that's because it is being split by 1, 2, 3 neighboring hydrogens. The peak representing HB is a triplet because we have 2 neighboring blue hydrogens. Now the distance between each of these splits is completely the same. So we can actually use the J value pattern to determine if hydrogens are neighbors to one another. So this is an example again of an ethyl group. So in our ethyl group, we have the 2 blue hydrogens splitting the red ones and the red ones splitting the blue ones. Now if we take a closer look at the distance between all of these splits, they are the same. So that means that these 2 groups of peaks have to be neighboring one another. Now, if we were to get an NMR spectrum, which contained a quartet and a triplet, however, the distance between the splits were different, it would mean that these 2 groups of peaks were not neighbors to one another. So this would represent a pattern that would not be an ethyl group. So complex splitting is very rare, but can occur when protons are split by non-equivalent neighboring protons. And again, similar to J values, this is not going to be something that is necessary for you to know or do when you're working on NMR problems in this class, but it's useful information that can be used to tell us what types of neighbors we have for a group of hydrogens. So in this example here, we have a group of 3 hydrogens, HA, HB, and HC. Now we're going to focus on HB in this example. HB is being split by HC. Now HC is next to group X, which could be electron donating or electron withdrawing, but ultimately is drastically affecting the electronic environment of these 2 hydrogens. HA is further away from X, so it's going to have a fairly normal chemical shift and electronic environment. So these are 2 very different hydrogens that are ultimately going to be splitting HB. Now HB is going to be split into a quartet by HA, and that's because HA contains 3 hydrogens. So N+1 says it'll be split into a quartet. It'll be split into a triplet by HC, and that's because HC has 2 neighboring hydrogens. Now, if JAB is much greater than JBC, the signal will appear as a quartet of triplets. And that means that the splitting between A and B is much greater than the splitting between B and C. So we will initially have the splitting into the triplet by HC, and then ultimately HA is going to take those triplets and they're going to break them up even further into a quartet. In our NMR problems, this type of splitting is rarely observed. Most often, we will observe this type of peak more so as a multiplet, so it would be a jumble of peaks with indistinguishable splitting.